Assalamu alaikum. How you doing, guys? Today's class is going to be a continuation of what we did last Thursday. If you remember, we said that the nominal shear Vn is equal to V alt Vc plus Vs. We covered Vc in detail last Thursday, as I said, and today we are going to talk only about Vs. Okay, so it says here, at each section where V ultimate is larger than 5 VC, transverse reinforcement shall be provided, which means that if V ultimate is larger than 5 VC, I need VS. And VS is going to be simply V ultimate minus VC divided by, or V ultimate divided by 5 minus VC. Okay, and from that I can find the value of VS. And if you remember last Thursday, we also talked about how to calculate VS, and the code is referring to this section right here on how to calculate VS, which is similar to the equation that we developed already. Now, if we have bent up bars, then this is going to be calculated from this section right here, which I also showed you last week how to get it. So I'm just going to reference those when we get to them. But what I want you to know is if V ultimate is larger than 5 VC, then I need shear reinforcement. Now, if I have more than one type of shear reinforcement, so let's say we have a stirrup, and if this is my stirrup and I have a bent up bar, for instance, then the total VS would be the addition of this bent up bar plus this stirrup right here. So this is pretty much what this section says over here. The types that are allowed, I can use stirrups, ties, hoops, as long as they are perpendicular to the longitudinal axis of the member. And when I mean longitudinal axis, this is my longitudinal axis, and these are the stirrups that are perpendicular to this axis right here, which is which is your main reinforcement. I can also use welded wire reinforcement. Again, they have to be perpendicular to my longitudinal axis of the member. And actually, at this point, I would like to introduce, so if I have a member like this, and let's say this is part of my beam right here. All right, so to me, this is longitudinal. Excuse me, G, all right? And this is what I call the transverse direction. So whenever you hear transverse direction, this is the direction that I'm referring to. If I say longitudinal direction, then this is the direction that I'm referring to, okay? So we talked about the welded wire reinforcement. We can also use spiral reinforcement, and I'd like to show you the types on the next slide. So these here are my stirrups, usually. And just to let you know that when I say stirrup or tie, then the only difference is that a tie, I'll be using that in a column, while stirrups, I'm going to use them in a beam, and they're practically the same thing. It's just different naming convention. Okay, spiral. This is how the spiral looks like, and they are also usually used in columns as well. If I'm talking about spacing in columns or between half, this is usually my spacing S. If I'm talking about spiral, then this is my spacing right here, and we usually call that pitch. As far as welded wire goes, this is what I mean by welded wire, and these are here my weld points. Okay, and you can find a slew of information on that on the web, on the designations, the diameter, but in this course I probably will not use any of that. I will be only concentrating mainly on the vertical stirrups right here, and when we get to the columns, we'll be using the ties and the spiral. All right, so this is for the types of reinforcement. So on this slide, we're showing how to calculate VS. To be more accurate, actually, how we are going to calculate the spacing. Because VS, we already had that from V ultimate minus 5VC. So this value to me is known. This is usually the area of the stirrup, usually one leg or two legs, depending on their crossings. So if I have this cross section right here, and I have a vertical U stirrup like this, so in this case AV would be the area of this one plus the area of that one. All right, so in this case it would be 2 times the cross section. So if it is phi 8, just simply pi d squared over 4, and the diameter will be either 8 or 10. Now if I add another leg over here, okay, then in this case it would be 3, not 2. Fy is the yield strength of steel. So if it's grade 60, it's going to be 420. If it's grade 40, it's going to be 280. D is the effective depth as usual. So the only unknown to me is going to be S. Now again, S for a spiral is usually the pitch, as I said. And also I forgot to talk about this over here. Here's just telling me that I could actually use inclined stirrups provided that the angle is at least 45 degrees. Not that I see that I've seen many of them. Mostly we use vertical stirrups. Now if I have an angle alpha, and again, and I've shown you this before as well, and this is for whether it's inclined stirrups or bent up bars, then again I know Vs, and the only unknown to me is going to be the spacing. Okay, I already talked about the effective area in the previous slide, and for circular ties or for columns, AV is usually 2 times the area of the bar, or wider than the spacing S. So this is always going to be 2 times AV, regardless. All right. Moving on. Now, in this case here, it's telling me if I have a bent up bar with an angle alpha that is at least 30 degrees, so it's not 45, so it's between 30 degrees and 45. So I can then, the only distance that I'm allowed to use is what I call the center 3/4 of the inclined portion. And if I look at this diagram over here and concentrate on this portion right here, then my maximum distance is d2, or d over 2, I'm sorry. So 3/4 of that will be 3 times d over 2, and that will be 3/8 of d. So if I have a crack that is inclined at 45 degrees, then the total spacing, or the maximum spacing that I'm talking about, is this distance right here. All right. So if I know this height, which is 3/8 over d, then tan alpha would be equal to this divided by that, with this being my unknown now, and this will come to 3/8 d cotan alpha, and since this is 45 degrees, then this is going to be 3/8 of d. So the maximum spacing for an inclined bar is this. Now if alpha is 45 degrees, then this will become 1, then the maximum spacing would be 6/8, which is 3/4 d. All right. In this portion right here, it's just telling me that the maximum spacing, well, should not be more than d over 2, and I will get to that in the coming slides with more details. So now here, it's telling me if I have shear reinforcement consisting of a single bar or a single group of parallel bars having an area AV all bent up the same distance from the support. So if this is a portion of my beam over here, and this is my support, and then all of them are bent up this way, and I have then I can say that my Vs is going to be the minimum of AV Fy times sine alpha, or 0.25 square root F prime C B web times d. Now if I have, on the other hand, if they consist again of a series of parallel bars at a different distance from support, so this is one and then this is the other one, All right, then instead of using these two equations, then I can use the equation that we have talked about before, which was AVFY sine alpha plus cosine alpha times D times S, which is the old equation or the previous equation, and you can find that equation on this part right here. Now we are going to talk about minimum shear reinforcement. So what we covered up so far up to this point is when V ultimate is more than 5 EC. So what happens now if V ultimate is less than 5 EC but bigger than or larger than 5.083 lambda square root F prime C B web VD, then I have to provide a minimum area of shear reinforcement. Okay, except for the cases in this table right here, and I'm going to get to that. But just that you know, this is what used to be in the old code, the ACI 14 code. This was supposed to be 5 VC over 2. Okay, now usually when we use 5 VC over 2, we only had the simple equation of 5 VC or the detailed equation, but now with the new code, as I said, we have like 3 different equations, which were equation A and equation B in that table that we talked about. So now this is becoming more specific to equation A, which is almost close to 5 VC because the simple equation was 0.17 lambda square root F prime C B web times D, which is a little bit more than 0.083. But again, this is now on the new code, and they're using 0.083 instead of the 0.085 that they used before. Not much of that difference, but at least I want you to know the relation between the two, between the old and the new code. Just to emphasize, this is according to the 2019 ACI code. Now, the exception in this table is here I will provide AV minimum only when V ultimate is larger than 5 EC, whether it's equation A or equation B. Okay, if it's not, then you could actually don't need to provide any shear reinforcement. It's not recommended, but according to the code, you could. So if I have a beam with a shallow depth, H, less than 250 millimeter, then I don't need reinforcement, provided that V ultimate is less than this value, that V ultimate is less than 5 EC. Okay. If it's integral with a slab, then if H is greater than 2.5 the thickness of the flange, or 1/2 the thickness of the web, and the depth is less than 600 millimeters, again I will not read any reinforcement, provided V ultimate is less than 5 VC. Okay. As far as the one-way joist system is, which is basically your rib slab, when we get into the part of the slabs, then I will talk more about this right here. If I have a beam or a slab constructed with steel fiber reinforcement with concrete, and F prime C is less than 40 megapascal, and H is less than 600 millimeters, and V ultimate is less than 0.17 square root F prime C B of D, I don't need any reinforcement. Okay. Moving on, if shear reinforcement is required, okay, then AV minimum over S, which is right here, again S being the spacing, should be the greater of 0.06 square root F prime C B web divided by FYT, which is again the grade of, or the yield strength of the steel used. It could be 420 or 280, depending what type of shear of steel you are using, or 0.35 B web over FYT. I'm not going to talk about the pre-stressed part. I'm just only going to concentrate on the non-pressed pre-stressed, since we're not talking about pre-stressed concrete over here. So my AV minimum should always be this, and I will show you in the summary page how we are going to use this information right here. Now on this slide, I'm be talking about the maximum spacing, and this is regardless of whether I'm using minimum or required. So this needs to be reinforced. And these have two parts. The first part, if Vs is less than 0.33 square root f prime c b web times d, then I have to use the lesser of, which means the minimum of, d over 2 or 600 millimeters. Now, if Vs is more than 0.33 square root f prime c b web times d, then I will take the lesser of d over 4 and 300 millimeters. So it's just half the value that's up there. The other thing that is interesting, or actually new in the ACI 19 code, is across the width. So if I have a cross section like this, and this is, let's say, my width B, and then I have my regular stirrup over here. Now this distance should not be more than D. Okay? Now, if it is less, then I have to add an additional stirrup, maybe somewhere in the middle, maybe right here. Could be a tie. Then if it's less than 0.33 square root, then this, instead of being d, now it will becomes d over 2. So the maximum distance between these two should not be more than d. Okay? For bent up bars, now instead of being d over 2, this was simply 3d over 4 if it's less than 0.33. If it's more than 0.33, then it will become 3d over 8. And actually, this is what I was talking about before, which is the 3D over 4 and the 3D over 8. So this is just talking about what we said previously, and I just added the drawing down here just to confirm that. Now, to summarize, and this is what you really want for solving the shear. So, and this is again provided when I have no axial forces, and this is exclusively for vertical stirrups. Again, no axial forces. So, first of all, we said if V ultimate is more than 5 EC, then shear reinforcement is required, or what I call a must. Again, if V ultimate is bigger than or larger than 5 EC, then shear reinforcement is required or a must. Now, 5 EC, I can calculate it from two equations. The first one is this, which we called equation A, and this is what used to be the old simple shear equation in the ACI 14 code, or the new one right here, which is 25.5b, and the only addition here is the square root of rho web. Okay, the cubic root of rho web. So again, in the code, it does not say which one you should use. It says or. So even if one of them is larger and you wanted to use the lesser amount, you can. Okay, if you only want to use the simple one, you can do that too. You wanted to use this one, that's fine. So there is no limitation on which one to use. I mean, it doesn't say whether you use the larger one or the smaller one. If it were up to me, preferably, I would probably use the lesser one just for more safety, but that's just me. So again, if V ultimate is larger than 5EC, and 5EC could be calculated either from this equation or that equation, one of them, okay, then shear reinforcement is required. Then Vs is simply V ultimate, which we are getting from the loading, minus 5EC, which is either this equation or that one, divided by phi. Then the spacing that I can calculate is supposed to be AV FYTD over Vs, which I got from this over here. So this is part one. Now, part 2. If V ultimate is less than or equal to 5 VC and at the same time more than 0.083 F square F prime C B web VT, which is what we used to call 5 VC over 2 in ACI 14, then shear reinforcement is a minimum. So here I have to provide a minimum shear reinforcement, and that, from the table that I showed you before, comes from calculating one of those two, and from these two you get the minimum distance. So if S1 is less than S2, you use S1. If S2 is less than S1, then you use S2. Again, this is AV minimum. Again, we know this value because beforehand we made the decision whether we're going to use a phi 8 stirrup or a phi 10 stirrup. Square root of prime C is known, B web is also known, so we can calculate these two as well. All right. Now, if V ultimate is less than or equal to 0.08, right, B, and this is the new equation in the AC19 code, C, so it has to satisfy both. Okay, these two must be satisfied. Then shear reinforcement is not required. All right, so the trigger, first of all, is this. So if it's less than that and less than that, I don't need any shear reinforcement. Again, it is not recommended, but according to the code, you do not need any shear reinforcement, period. So you have to satisfy both these two equations, and this is what we call equation C from calculating phi VC, and we talked about that as well. And I'm just re-emphasizing this, and I put it in bold. If shear reinforcement is used, regardless of whether it is minimum or required, then the below must be satisfied. And we talked about that a slide ago. All right. So I'm going to stop here today, just to give you some time to digest what we talked about. The next class I will follow up on examples, and it's going to be probably 2 or 3 examples, if not 4. Again, if you have any questions, as I said, on e-learning, feel free to email me. Thank you and have a very nice day.